Welcome to part 2 of our lesson on second-order ordinary differential equations. Today, we will extend the basic numerical methods we learned previously to model more realistic physical systems, specifically focusing on damped and driven oscillators. We will also learn how to interpret various diagnostic plots to ensure our computational models are physically sound. By the end of this session, you should be able to write and solve first-order systems for damped and periodically driven oscillators. You will also learn to interpret displacement, velocity, phase space, and energy plots, and we will review common pitfalls to avoid when solving these equations numerically. Let us briefly recap the core strategy from part 1. When faced with a second-order ODE governed by acceleration, we introduce a new variable for velocity, defined as the first derivative of displacement with respect to time. This allows us to rewrite the single second-order equation as a system of two first-order equations, which our numerical solvers can handle. To implement this in Python, we start by importing our essential libraries. We need NumPy for array operations, matplotlib for visualizing our results, and the solve_IVP function from SciPy to perform the actual numerical integration. We also set up a local cache directory to ensure our plots render smoothly. We will now introduce damping into our harmonic oscillator model to represent the loss of mechanical energy, typically due to friction or drag. The equation now includes a term proportional to the velocity, governed by the damping coefficient gamma. Rearranging for acceleration gives us the expression needed for our first-order system. In our Python code, we define the damped oscillator function to represent this system. It takes the current state, unpacks it into displacement and velocity, and calculates the derivatives. The rate of change of displacement is simply the velocity, and the rate of change of velocity is our new acceleration formula, which now includes the negative damping term. Let us compare how different strengths of damping affect the motion. We will look at 4 distinct cases: undamped, underdamped, critically damped, and overdamped. We set up an array of these gamma values to iterate through, keeping the initial displacement at 1 meter and starting from rest. Here we loop through our chosen damping coefficients, calling the solve_IVP function for each case. Notice how we pass the current gamma value into the solver using the args tuple. We then immediately plot the resulting displacement over time for each scenario, building up a comparison on a single graph. This final block of code simply adds the finishing touches to our plot. We set the grid, display the figure, and prepare to examine the visual results. This visual check is crucial for understanding the qualitative differences between the damping regimes. The plot clearly illustrates the effect of damping. The blue curve shows perpetual undamped motion. The orange curve shows underdamped motion, oscillating with a decaying amplitude. The green and red curves represent critical damping and overdamping, respectively, both returning to equilibrium without crossing the axis, though critical damping gets there faster. To summarize, the physical interpretation is quite clear. Underdamped systems still oscillate while losing energy, whereas critically damped and overdamped systems do not. In engineering and physics, designing a system to have a specific damping profile is vital. For instance, to stop a car suspension from bouncing endlessly. Another powerful way to validate our damped oscillator model is by looking at the mechanical energy. The total energy, which is the sum of kinetic and potential energy, should decrease over time, as damping does work on the system. Let us set up an underdamped case with a gamma of 0.25 to verify this. After solving the system, we extract the displacement and velocity arrays. We set the mass to 1 kilogram for simplicity and calculate the spring constant. Then, we compute the total mechanical energy array using the standard formula. We first plot the displacement and velocity together to observe the decaying oscillations. Next, we prepare a second plot specifically for the mechanical energy. We plot the calculated energy array against time. This diagnostic plot will help us confirm whether our numerical solution obeys the expected physical laws regarding energy dissipation. Looking at the first output, The displacement and velocity curves show the expected underdamped behavior. Notice that the velocity leads the displacement, and both amplitudes decay smoothly over time. The numerical result looks physically sensible. The second output confirms our energy expectations. The total mechanical energy starts at a maximum and steadily decreases towards zero. The slight ripples in the decay occur because energy is lost most rapidly when the velocity is highest, which happens twice per oscillation cycle. This energy diagnostic is highly recommended. If you ever simulate a damped system and find the energy increasing or remaining constant, you immediately know there is a flaw in your mathematical model, a bug in your code, or that your solver tolerances are too loose. Let us move on to the driven damped oscillator. We introduce a continuous periodic driving force, represented by a sine wave with an amplitude A and a driving angular frequency omega d. This modifies our acceleration equation, adding a positive forcing term to counteract the energy lost to damping. We update our Python function to calculate the driven damped oscillator. The state unpacking remains the same, but the derivative of velocity calculation now includes the external driving force. This structure allows the solver to continuously update the acceleration based on the current time, displacement, and velocity. When a driven oscillator starts from rest, its motion is initially complex, known as the transient phase. Over a long time, the damping removes this initial erratic behavior, and the system settles into a steady-state oscillation dictated by the driving force. We will simulate this over a longer time interval of 60 seconds. We call the solver with our chosen driving parameters and extract the time, displacement, and velocity arrays. We then create a plot of displacement versus time. This will allow us to visually separate the initial transient response from the eventual steady-state behavior. We also prepare a phase space plot, graphing velocity directly against displacement. Phase space plots are excellent for identifying repeating steady states, which appear as closed loops. These two plots together provide a comprehensive view of the oscillator's dynamics. In this displacement time plot, you can clearly see the two stages. For the first 20 seconds or so, the amplitude fluctuates erratically. This is the transient behavior. Afterwards, the system settles into a smooth, constant amplitude oscillation, demonstrating the steady-state response to the external drive. The phase space plot shows the same transition from a different perspective. The trajectory starts at the origin and spirals chaotically before eventually locking into a stable, repeating elliptical orbit. This stable loop confirms that the system has reached its long-time steady state. Next, we explore how the oscillator responds to different driving frequencies. We expect a resonance phenomenon where the amplitude peaks when the driving frequency matches the natural frequency. We write a helper function to estimate the steady-state amplitude by looking only at the final 40% of the simulation data. We set up a loop to test 13 different driving frequencies. Inside the loop, we solve the initial value problem for each frequency. This approach allows us to automatically gather data across a range of parameters, without writing repetitive code for each individual case. This code finalizes the parameter scan plot. We set the axes and labels to display the estimated long-time amplitude against the driving angular frequency. The resulting graph will serve as our diagnostic for resonance. The output reveals the resonance curve. As expected, the steady-state amplitude reaches its maximum when the driving frequency is very close to the natural frequency of 2 radians per second. The peak is slightly shifted and rounded due to the presence of damping. This exercise demonstrates the value of parameter scanning. By automating the evaluation across a range of frequencies, we captured the broader physical phenomenon of resonance, rather than just observing a single isolated trajectory. As computational physicists, we must always validate our results. We should check that the initial conditions are respected, test limiting cases like zero damping, and monitor energy conservation. Let us look at one specific numerical issue: the effect of output sampling on our plots. By defining a coarse and a fine time array, we run the solver twice for the same physical system, once requesting output at the coarse time points and once at the fine time points. We then plot both results together. It is important to understand that the solver adapts its internal steps accurately in both cases, but the data it returns for plotting depends on what we ask for. This line commands matplotlib to display the comparison between the two sampling densities. We will see how a lack of output points can distort the visual representation of the physics. The plot clearly shows the danger of coarse sampling. The orange dots miss the peaks and troughs of the oscillation, creating an illusion of a jagged, lower frequency wave. Always ensure your evaluation array has enough points to smoothly resolve the highest frequencies in your model. Let us review some common mistakes. The most fundamental error is trying to feed a second-order equation directly into the solver. You must always reduce it to a first-order system. Additionally, remember that a second-order system requires two initial conditions in the state vector, not just one. Another frequent bug is mixing up the order of variables in the state vector or the return derivatives. If your state is displacement then velocity, you must return them in that exact order. Also, ensure all physical parameters have consistent units, such as radians per second for angular frequency. Finally, do not rely solely on a single displacement time plot. As we have seen, phase space and energy plots provide deep insights into the stability and physical correctness of your numerical solution, helping you spot errors that might otherwise remain hidden. Let us try some guided practice. We will set up a new driven damped oscillator scenario. By changing the damping coefficient, the driving frequency, or the initial conditions, we can observe how the system adapts. We define a new set of parameters, changing the initial displacement to 1. We run the solver with these modified practice parameters. We then extract the data and plot the displacement over time. Changing the initial conditions should primarily affect the early transient phase, while the long-term steady state should remain dictated by the driving force. We finish by preparing a phase space plot for this practice run. This will help us visualize how the trajectory moves from the new initial state at a displacement of 1 and velocity of 0, and how it eventually spirals into the steady-state limit cycle. The resulting displacement plot shows that the oscillator starts exactly at a displacement of 1. The initial transient phase looks different from our previous example, but if you look closely at the right-hand side of the graph, it settles into the exact same steady-state oscillation pattern as before. The phase space plot confirms this. The trajectory begins at the coordinate 1, 0 on the right side of the plot. It loops inward during the transient phase and eventually merges into the exact same central elliptical orbit, demonstrating that the steady state is independent of the starting position. To summarize, second-order ODEs are vital for modeling physical systems governed by acceleration. The key workflow involves rewriting the equation as a first-order system, defining the state vector correctly, choosing sensible parameters, and critically validating the numerical output using physical principles like energy and phase space diagnostics.